Hello Math 126 students. Wanted to do a video where I do one extra example of global max and min from 14.7. This is often a topic students ask about. We will do an example in class, but they take a little while, so I just thought I'd post an additional example in case you needed a little help or extra summary or just wanted to review. I'll try to keep this as short as I can. So global max and min question is saying, what is the biggest that can come out of your function? In Math 124, we do these questions quite a bit, and we talk about the following idea, which is if someone gives you an interval, and when you have a picture, you can see it. But if someone gives you an interval and says, well, what's the biggest y can be? It can only be in one of two places. Your eyes know this already. They're going to be here or here, which is an endpoint, or it's going to be a critical point. So this method isn't so elegant, it just works. Meaning, if you know where the endpoints are, and you know where the critical points are, just plug all of them into your function and see which makes y is the biggest, because it's got to be one of those. That's the whole idea. Now, in multivariable calculus, it's a little harder because there are more endpoints. There's not just two. Here there were only two endpoints. In multivariable calculus, you're going to have a region on the ground, and if you have a region on the ground, there's an infinite number of endpoints to check everywhere along this edge. That's trouble. Okay, so here's what we do. We draw the region, that's the big thing, and then we find if there's any critical points inside the region. That's like in 2D, that's like finding critical points. If you have a critical point that's outside the region, we don't care about that, because the question is going to be saying what's the maximum over the given region. And then we do the boundary. And we go one by one across the boundaries. It turns out for each boundary, you can do a one variable calculus problem, So I'm going to go through and do that. It's more of a process. If you can just get all the steps down, it's not too bad. Sorry, it's just scrolled away. But it's really just trying to reduce the number of things we need to check. And then in the end, the key thing about a global max and min question, or absolute max and min, is in the end you plug in to your original function, not to the second derivative, not to anything else, because the global max and min question is saying what is the biggest output from the function. And so you have to plug in. So here's a question straight from an old test. This is in my notes, but I probably won't do this one in class, so I thought I would do it here. So the question says, find the global max and min of this over the following region. Now, if you prepare, this should not be so bad of a question on a test because it's very formulaic. And what do I mean by that? First, you're going to see if the function itself has any critical points. Now, it does help to sketch a little bit, so I'm going to do that now. You do want to realize that y equals 0 is just here. So here's y equals 0. Y equals 0. And then separately, we have, what color to use? A parabola, a sad parabola. The picture itself doesn't help me that much, but I'm just mentioning this is the region. It says consider this region that's bounded by this. This is x, this is y. So what we're considering in this problem, it looks funny when you go to draw it on the ground, but what we're considering is this region. And then above it we have a surface. And the surface is this weird messy formula they gave. Z equals x squared plus 4y minus x squared. And in the end, we're just going to see what the biggest z can be. Okay? Again, it's not elegant. What we're going to do is we're going to see if there's any critical numbers on the inside, and then we're going to look at all the points on the boundary in a systematic way. Okay, so let's first talk about, see if there's any critical points. This is more about organization than anything else. So on a test, I would want to see someone say, okay, I'm going to compute the partial with respect to x, 2x minus 2xy. I'm going to compute this partial with respect to y, 4 minus x squared. I'm going to set equal to 0. If there's anything I can factor, I'm going to do that. So 2x, 1 minus y is 0. And then you're going to combine and solve. Okay, I think if I was doing this, I would start with equation 2. If I start with equation 2, there's two possibilities. X could be negative 2, or x could be 2. And then if I plug this in to the first equation, I think you get y is 1. If I plug it into the second equation, I think you get y is 1. So there's two critical points, negative 2, 1, and 2, 1. Interesting, I guess I didn't plot here, but if y is 0, where do they intersect? So I'm curious if those are in my region. Well, let's see. You'd have 0 is equal to 2 minus 1/2 x squared. You'd have 2 equals 1/2 x squared. You would have x squared is 4, so x is 2. Oh, that's 2. And that's negative 2, which means 2, 1 is like out here. Negative 2, 1, and 2, 1. That's not in the region they're talking about. So I don't really need to do anything else with those. If the question was a local max or min question, or I could figure out, is it a saddle point, is it a local max or min? But that's beyond the scope of the question. The question is just asking about here. So the entire question now is about the boundaries. And there are two jobs. One job is to plug in all of these points to the function. Well, how are we going to do that? And the next job is to plug in all the points on the curve. So there are two boundaries, so to speak. And you need to write down what they are. So the first boundary is y equals 0. And the second boundary is y equals 2 minus 1/2 x squared. And I could even say a little more. Not only is it y equals 0, but I know that x is between 2 and negative 2. And I also know here that x is between 2 and negative 2. Okay, so we've talked about what it means to be a point on here and what it means to be a point on there. We need to somehow plug all of these points into my function. You go, well, that's complicated. How are we going to do that? We can't plug in it. We can. If you take any point from this side, x, y, we know that y is 0. I just need to plug that in up here. You say, well, I don't know what x is. That's true, but just leave it as x. So you're going to say x squared plus 4 times 0 minus x squared times 0 plus 1. And then you're going to get z is x squared plus 1. And the moment after you do that, you now have an interval and a one variable function. We can now do one variable calculus. So this is the hard part about this, is for each side, you're going to do a one variable calculus problem, which is what is the maximum of that one variable function over that interval. So if you've forgotten how that goes, the maximum of a one variable function is at the endpoints or at a critical number. Not critical point, but critical number, a place where the one variable function is 0. So there's a systematic approach to answer any question like this, which is you take the derivative of the one variable function. Notice I used a prime because there's just one variable. And you get x is 0. And then the way you solve these questions was you plugged in the endpoints and the critical numbers to the one variable function. So you say, okay, what happens if I plug in a negative 2? I get 5. What happens if I plug in a 0? I get 1. What happens if I plug in a 2? I get 5. And I know on this side that one of those has to be the maximum. So this is the key. I don't actually have to plug in all the points on the side, but I do have to plug in the endpoints. Now if you're looking back at the picture and you think about what those correspond to, two of those were corners. Sometimes students get confused and they say, okay, you're saying just check the corners. No. The corners will always get checked because they're endpoints. We've just found out that z is 5 here, and we found out that z is 5 here. But we also found out that there's a point here, z is 1. And we found out we don't need to check anything else on that side. That's the key. We are done with that side. So it's, like I said, it's mostly about organization. So you just go, okay, for each side, I'm going to do a one variable calculus problem. And how do we do one variable calculus problems? We take the derivative, set equal to 0, and we plug in the endpoints and the critical numbers. Now we're going to do the same thing on this side. So then you go back and you say, I need to plug this in. So if I have a point that's on this side, this is the relationship into here. Ooh, that looks bad. So you're going to replace y this time with 2 minus 1/2 x squared. So I just replaced y and replaced the other y with 2 minus 1/2 x squared plus 1. And now you're back to doing a one variable calculus problem. This is what it means to be a point on the surface that's above a point on that side. I know it's a bit to think about. So we're going to completely simplify this. Plus 8, just because I know I might want to do a little more, minus 2x squared plus, is that x to the 4th plus 1? Oh my goodness. So we get x to the 4th minus 3x squared plus 9. And then you go, okay, I'm almost done with the problem. I know that I need to plug in the endpoints. Now the truth is you don't have to plug in the endpoints because we already know the value is going to be 5. But if you wanted to double check your work, you could plug in a 2 here and see that you get 5. Because this is the endpoint of both of these curves, the line and the parabola. So you could double check. When x is 2, you get z is 5. When x is negative 2, you should get z is 5. So you can try that and see what you get. You can get 25 times 25 minus 3 times 25 plus 9 and see what you get. Is that 5? I guess we could factor and see. But let's keep going and see. Okay, so the other thing you have to do is take the derivative of that one variable function. I'll pull up the solutions in a second so you can see the full calculation. And then we need to know when that's 0. Why am I doing that? Because that's how you do a one variable calculus problem. For a one variable function, its maximum is either at an endpoint or a critical number. And this factors into 2x, 2x squared minus 3. So I get x equals 0, or x squared is 3 halves. So I get x is plus or minus the square root of 3 halves. Okay, so on this side, I need to consider the point on this side where x is 0. I need to consider the point on this side where x is negative the square root of 3 halves. I need to consider the point on this side. So you could actually find the x and y coordinates of those, or you could plug these in here. Either way, if you plug in 0, so at 0 you get 9. So I know that this is z equals 9, which is currently the winner. That looks like the biggest so far, because this was 5, this was 1, this was 5. That's 9. And then I need to plug in the square root of 3 halves. What's that going to be? Well, that's going to be negative 3 times 3 halves plus 9. Just trying to plug this in here. And this is going to be 3 halves squared, so 9 fourths. So I think that's 9 fourths minus 9 halves plus 9. Oh, what do we want to do here? This is going to be, let's make them all fourths. 9 fourths minus 18 fourths plus 36 fourths, which is going to be 27 fourths. 27 fourths is z. At that point, I'm done. I know I've kind of been disorganized, but you could go back and say, okay, what's the biggest of those? The biggest of those is z equals 9. What's the smallest of those? Z equals 1. And as long as you've checked any critical numbers from the inside, plug them into your function. And I am plugging into the function when I'm computing z here. You could take your point and plug back into the original function, but this is the function with on this side. So this is the max. This is the min. On a test, what do you have to do? You get most of the points on the test if you write this, this, and this. That's what I want to see. So make sure on a test you actually write those things. I want to be clear that you, because sometimes people like guess one of the answers or something, but I want to see that you know, okay, I need to check all the points on one boundary, all the points of the other boundary. I want you to actually give the function if I ask this question. Let's take a look at a couple things. So first, some visual. So here's what we just did. That's the surface. The actual surface is this. And if you were to look at it, I think it has a saddle point somewhere over here and a saddle point over here at negative 2, 1. Those are the points. But the question wasn't about those. The question said, I only want you to look at it above here. So again, they gave us a region on the ground. Let me remove so you can see it. There's the region on the ground. Okay, so what we figured out is that the surface itself doesn't have any maxes or mins in the region. If you were to graph it, there is no max or min there. That just keeps going down. Okay, so that told us that there were no critical points in the region. So then we switched to studying the boundaries. First we studied this boundary. How did we do that? We plugged in 0 to our function. Again, here's our function. There's what happens when you plug in y equals 0. You just get this parabola. And that was the parabola x squared plus 1. And we said for that function, x squared plus 1, we had to plug in the endpoints, which we did, and we got 5. You can see it right there. And we have to take the derivative and find what equals 0. And we got 0. We plugged in, we got 1. So the minimum was 1. The maximum was 5 on that side. That's what we were doing in our work. That's what this work was. When we plugged in 0 and got x squared plus 1, we were looking at that side. So hope that visual helps. Okay, so then what do we do? Then we plugged in the parabola. Now this is sort of weird. We said if you take any point on the edge here and plug it into your surface, you're going to get a curve. It actually is a 2D curve. Every point on there, you can think of it as you look at it from the side as a function of x. And then we can say, okay, where are the low points and the high points on this? Turns out there were 2 bumps and there were 2 endpoints. Now the endpoints are 5 because it's the same endpoint. But we had to find where those 2 spaces were. And we did. We found out that this was at negative square root of 3 over 2. This was at positive square root of 3 over 2. And that was at 0. So then we plugged those in and we found out when you plugged in 0, you got 9. I'll make it so it actually lines up with our axes. What really was happening was this. We found out from here to here it was 9. But what we learned is we didn't need to plug in any other points besides those critical points we found. So at the end of the story, we found out that the answer had to either be here, at this critical number on this side, or an endpoint, or it had to be here, here, or here. And we reduced it down to just 1, 2, 3, 4, 5, 6 points we had to check. Which is pretty good, going from an infinite number of points to 6. And we found out the lowest overall is down here, the highest overall is up there. Okay, so we aren't going to do a lot of that, but it does help you think about some of the differences. This is the biggest difference between one variable calculus and 2 variable calculus is there are a lot more endpoints. All right, I hope that helps. So when you go to do the homework examples are all kind of special examples, but your job in all of these problems is really about the boundaries. So when it says absolute value of x is between 1, is less than 1, that really means x is between negative 1 and 1. So the picture of your region for this first question is this box. And to me, this is the hardest of the questions here because you have 4 sides. Oh my gosh. 1, 2. Now each of the sides have a fairly quick analysis. I think one or two of the sides is a little longer, but you're going to have to consider, I don't know, y equals negative 1. The order doesn't matter, but you're going to have to do this side. You're going to have to do x equals 1. That's this side. In particular, you're only looking at between here and here. So you have a bunch of small jobs to do. And this is particularly bad because there are 4 sides to the story. There's another side. And then the last side, I think that I haven't mentioned yet, is x equals negative 1. Okay, so what you're going to do when you're going to study this side is you're going to put a 1 in here. You say, okay, that's basically what happens when I plug in any point on this side. There's going to be a 1 in place of the x, which means I'm going to have a z equals 1 plus y squared plus y plus 8. And now you get to do a 1 variable calculus problem on this interval. So you're going to plug in negative 1, you're going to plug in 1. Now some of these points you don't have to plug in multiple times, just once will do. You also need to see if there's any critical points inside the region. Same thing with this one. This one is saying I want inside the circle and in the positive axis. So this is saying, okay, this would be root 3, this is root 3, there's the region. So this time you have 3 things, 3 boundaries. You have y equals 0 between 0 and root 3. You have x equals 0 for y between 0 and root 3. And then you have this equation, x squared plus y squared is 3. And it's also between here and here. Now this one's kind of nice because of the fact that you can write y squared is 3 minus x squared. And so when you go to substitute, I think it simplifies pretty nicely. In fact, it's really weird. When you plug in y equals 0, you just get 3. When you plug in x equals 0, you just get 3, which means every point on this side corresponds to something that's a height of 3, and every point on this side corresponds to something that's a height of 3. So there's really just one side you have to consider. So plug that in, and then you have a one variable calculus problem to do. Right, so the function is z equals x, 3 minus x squared plus 3. You know that x is between 0 and root 3. I'm getting that from the picture. Can you solve that one variable calculus problem? What's the maximum minimum that that one variable function could be? So now we're jumping back into calculus 1. And we need to figure out, we're going to have to plug in the endpoints, the 0 and the root 3. We're also going to need to take the derivative, see if the derivative is ever equal to 0. That's the game. Same thing on this one. This one's talking about the entire circle. One thing about when you're working with the entire circle, it's really, if you solve for y, you're going to have plus or minus the square root of 1 minus x squared. So sometimes it's good to realize to separate it in your mind. The only reason I say that is sometimes people go, for a circle, there's no endpoints. Well, technically there are endpoints. The biggest and smallest values you get are endpoints. So if you do it in terms of x, then -1 and 1 are endpoints. Okay, so there's those can be long, but so when you look at the solutions on old tests, you go, oh my gosh, these questions are terrible. But then when you sort of step back, if this was on a test, I don't think you should be upset if it's on a test, because you can immediately write down all the steps. And what do I mean by that? Well, in this question, you would do the critical points on the inside, but that was in the previous part. And then you can see all I did was, okay, one side is y equals 0, plug it into the function. One side is this, plug it into the function. So they look like a lot, but they're not as bad as they seem. Usually people do pretty well on these on a test. I don't ask it on every test, but I do ask it quite a bit. So let's look and see. Unlucky. Let's try one more. There's a local max and min. Okay, here's a global max and min question. Notice the key things in the solution, which is, okay, what are the boundaries? The boundaries are y equals 0, they told me that, y equals x squared, and x equals 4. So your first job would be to figure out what that looks like, where the intersections are. But I need to plug in y equals 0 and talk about what happens. Well, in this case, when I plug in y equals 0, you just get 0. So that side is done. Because your goal is to get the z values for each side. And if it's just a constant, you don't need to do any more work. 0 is the z value for all the points on this side. Then you go to x equals 4. So now I want to plug in x equals 4 here. That's going to give me z as negative y. Now, the truth is that's linear. You could take the derivative and set it equal to 0 and you'd get no solution, which is actually good because that means the only thing you have to consider is the endpoints. So you plug in both endpoints to your function. The endpoints would be 0 and 4 for y. So from there I got, what did I get? When I plug in 4 for y, I get negative 16. 4 for y? Oh, sorry, y is 16. 16 is what I should be plugging in for y. That's why I was getting confused. You can see in this solution, I waited to plug in my numbers till the end. You can also plug them in as you go. Both are fine. Okay, and then the last side. Excuse me. Sorry about that. The last side is y equals x squared. We plug that into our function. It gives us a one variable problem. We want to know the max of that for all x values from 0 to 4. Take the derivative, set it equal to 0. I got two answers, 0 and 2. I could have plugged those in right here. It looks like I decided to go back and figure out the x and y value. So all three corners are accounted for. It's a nice little double check of your work. You should at some point plug in all three corners because they're the boundaries, the endpoints of the one variable functions. I didn't find any critical numbers on this side or this side, but I did find a critical number here, x equals 2. And if I'm at x equals 2 and on the boundary, that's 4. So that's what I did here, is basically I said, okay, these are the 4 points I have to consider. And so I plugged them in. I got that these gave me 0, this gave me negative 16, this gave me 4. So it's more about organization, but you can immediately write these things down and get them plugged in. You're just trying to systematically plug in all the endpoints. Now, the one other thing I didn't mention was you also need to check the inside, but when I took the parts with respect to x and with respect to y and solved, I got 3, 0. 3, 0 is a point on the edge. You can plug it in, but I didn't need to because I already knew that every point on that edge gave a value of 0. So that's why I didn't explicitly plug it in. It wouldn't be marked down for including it. The main thing people do is sometimes students get part of it right, but they completely leave off any mention of some of the boundaries, and there's going to be big deductions for that. So you do need to clearly show that you knew what you had to study, that these were the 4 things we had to study. Okay, hope that helps.